Alright, so welcome to our second challenge today. So today we're just going to undergo a simple reaction and we're just going to try and predict the products of this reaction. So here we have, what's this, 1, 2, 3, 4, 5, 6, this is, 3-methyl, 2-butanone, and we are going to react it with ethyl chloride under acidic conditions. So first, let's recall that ketone groups can undergo this process called keto-enol tautomerization. And even though for ketones, the keto group is more favored, the tautomerization reaction can still occur in part. So let's go ahead and draw that mechanism here. So first we have our initial product of the ketone, and it's undergoing tautomerization. So we're going to go ahead and move a hydrogen to form a hydroxyl group and an alkene, which is an enol. So now we're left with this product here. Finally, we have a lone pair on this oxygen. And this lone pair is going to reform the double bond, and at the same time, ethyl chloride is going to undergo dissociation. It's going to result in a carbocation and a chloride anion. So we are going to have this side product of the chloride anion and a positive carbocation on this ethyl group. And so this pi bond that is present in the alkene is going to attack the ethyl group, which is going to result in a nucleophilic substitution. And because this is attacking, we are also going to need to reform a bond for this carbon 1 connected to the alcohol group here. So, after that step, we're going to be left with this substituted oxonium, because the oxygen has 3 bonds in total. Now, this ethyl group, and we're going to redraw the rest of the hexane chain here. And let's remember our double bond and our positive charge on the oxygen. Now, oxoniums having an oxonium is not a favorable position for oxygen, and as you might notice, we already have this chloride right here, which is ready to accept a hydrogen. So, in this last step, the oxonium is going to simply be deprotonated by the chloride, which is going to give us our final product, where the chloride attacks the hydrogen in order to form the final product, which has a ketone group and our substituent. So we have our ethyl here, that's the methyl, and we have our original final bit of the hexane chain. And our side product is going to be hydrochloric acid, and that's our final product. This is not so much of a challenge, but it's more of just a review of nucleophilic substitution. Another important thing to recognize is that this is going to result in a racemic mixture of products, because this is a chiral carbon. Because remember that ethyl groups are equal to CH3CH2. So we have 4 different substituents at this carbon. It's going to have a racemic mixture. So we're going to be left with multiple products. That's all for this problem. The acidic agent is just there to help with the tautomerization. That's all we needed to include it for. So finally, we can rewrite this entire reaction with a ketone and go ahead and show the final product. There's the ethyl, and then that's like a propyl group, right? And there's the ketone under acidic conditions and with the ethyl chloride, of course. And there's our byproduct of hydrochloric acid. So I hope you guys enjoyed just that small little problem. Probably wasn't that hard for all of you. but it's always fun to go back and review basic reactions.